Okay, amazing. Hi guys. My name is Indy. I'm going to go over a bit more of an introduction about myself in a second, but this is my workshop from pit stop to podium. It's all about technical, complex project management for really large teams and large organizations. So this is a bit greater in scope than your small, projects. I lead a design team that I'll talk about. Yeah. So as I said, I'm Idan. I lead MITPIT RW. We're a joint team with members with partner schools at MIT, the University of Waterloo, University of Pittsburgh, and a Rochester Institute of Technology. But we have members from all over, such as Laurier and other schools like Penn, like UPenn in the US. And we compete in the Indy Autonomous Challenge, as I'll get into in the coming slide. And I'm also a published robotics researcher, so I do have quite a technical background. And now I lead this team of around 40 to 50 members. I studied mechatronics engineering at Waterloo, and you can connect with me here on LinkedIn. This picture over there is from us. We went to Monza, which is an F1 track in Italy, where we raced there in the first ever autonomous race. So this is quite high speed and really fun. A bit about this workshop. First, I'm going to go over an introduction about myself, my team, and what we do, so you have some context about what I'll be talking about. Then I'll go into what is a technical project manager. So as my role as a general manager, I go over, the technical aspect, technical architecture. Unfortunately, I don't write much code. I do like it, but I don't do that much anymore. But also the management side, the leading side. There's a lot to do when you have 4 partner universities. You're an international organization, and we are 100% student run. So we're all undergraduate students and competing against, labs that are fully funded and have a lot more time, resources, experience, and members than us. Then I'm going to be talking about KPIs. What is a KPI? That's a key performance indicator. How do you actually measure success? How do you actually measure how things are working? It's pretty easy to do when you have qualitative or quantitative information. That's information you have metrics on, you can measure. What do you do with qualitative information? That's a lot more difficult. So I'm going to be talking about that. Then we'll go over a case study. It'll be an actual experience that I had when I was in Las Vegas at CES racing there in January. Super exciting, and how we're going to go over, the different things and a bit simplified down, and then a bit of a conclusion, time to ask questions and chat. So let's kick things off. So this is the design team. This is Betty. She's our car. This was taken in Monza, and that was in Las Vegas, where I was there with actually my brother, who's also on the team. And yeah, we race all over the world, and it's at over 200 kilometers per hour. As you can see, it's not a small little race car. It is a full-size Indy Lights race car. This car has been modified with hardware to drive autonomously, and we write all of the code. We were one of the original teams that wrote the original stack that got the car moving. First, you move it with a remote control, which is pretty stressful because it's a manual car. You're controlling the gears with a Xbox controller. That's hard and stressful, and if you make a mistake, you screw the transmission, you can screw up the engine, or you can crash into a wall. And we built that up to now drive at over 200 kilometers an hour, fully autonomously with other cars on the track. So you have 2 cars going well over 200 kilometers an hour, passing each other. So this is just a quick video of our car that a Super Formula Drift race car driver wanted to post about us. Real experience. So that's just our car. It's the real deal. Real experience. Yeah. So as I said earlier, we can compete on tracks worldwide. We race at super high speeds. There's 40 to 50 members. We're across 2 countries and over 4 schools, and we're only student teams. So a bit about where we've raced and what does an actual race mean. So these stars are all the tracks we've raced at. So we've raced at CES, I believe, for 3 years now. We've raced in Texas, we've raced in Indianapolis, we raced in Goodwood in England on the famous hill climb. That's a climb up a hill with hay bales on the side. And then we've also raced on the Monza F1 track in Italy, the Temple of Speed. That have been, incredible experiences. But what does an actual race mean for us? It's not as simple as just getting the car to go, because, it's hard to get this autonomous car to drive by itself because you need to know exactly where you are. So the car is outfitted with many sensors. Some of them are, localization. What that means is, where am I with respect to my environment? Right now, I can see because I have eyes and have lived experience. I know I'm standing here in this part of the room, but if you're a robot, how does it know that? It's very hard to actually learn where things are. And that's why we have those types of sensors. So we have to make sure they're calibrated, they're working, and then we have to map up the track. It's very hard to just get on a racetrack and race. If you've ever driven on a road that you're not familiar with, it's a bit harder to drive than on a road you're familiar with. That's because on a road you know where it's going to go, you know where the turns, you know where the potholes are. On a new track, you don't. So what we do is we go for, I'll go for Italy. We were there for around 4 months beforehand. The first little bit was literally controlling the car with a remote controller or having it just trail our car. So we drove on the track and it just did laps and laps and laps. And what we did is we built a map. Now that we have a map, we know what it looks like visually. We know what it looks like in terms of depth, and we know what it looks like on the GPS. We put all that through an algorithm that makes a really robust map of the environment. So now we know we have a map, we know where we are within that map. And then we can race, and then we can go at higher speeds and do testing and test different algorithms, a different controller, different aspects of the car. And now make that an order of magnitude more difficult, put a second car on that's doing the same thing and trying to pass you or trying to defend their race line. And that's all what racing is. It's easier to do when you're a person, but training a car to do it is a lot harder. That's what a race is. A lot of race is testing and pushing and testing, and similar like to a hackathon, except stretch it over, weeks or months actually of continuous development at the track all day, every day. And you go wake up, sleep, wake up, work, sleep, repeat. So somehow I manage. What is a TPM? What does a TPM actually do? So the first is communication. This is one of the biggest roles for a TPM is communicating, making sure everyone knows what they need to know. So that is, making sure the technical team knows what other technical teams are doing. And that starts at the bottom. You want to make sure that your developers, your engineers know what their task is when talking to their leads, because sometimes in a big meeting, it's hard to fully identify exactly what you want. Then it's planning. You're responsible for the entire development cycle. So I need to make sure that, we want to implement a new way to figure out where we are on the track. How do we do that? How do we test that? Okay, now how's the timeline? Can we do this in time? What resources do the engineers need? A big role, again, is back to communication, making sure I know what resources they need so I can provide that to them. Then it's management. On my team, there's 4 engineering teams. There's over 6 weekly meetings and 80 plus repositories. That's where all your code is stored on a platform like GitHub. That's hard to manage. I am a full-time student or I'm on co-op and I need to manage that. So I cannot attend 6+ meetings. That's over 6 hours of work, 6 hours of meetings each week on top of other responsibilities that I have as a lead. So I need to know how to delegate. That's another huge role, and it ties back into communication and planning. You need to be able to delegate to your team and trust your team members. A big thing that we have on this team and I'm proud about is I trust every single member on this team. Down to the engineers, the leads, I know them all, and I know that if I ask them to do something, they'll tell me if they can or can't, and I trusted them to give me a good timeline because we work together. Because it all ties back into communication about knowing what's needed and how to communicate that. So a bit of an example is we're in Vegas and we're racing and we upshifted and the car stopped. That's not good. We didn't know why. We pulled the car in, we went out again, same thing. We have no idea why. I'm monitoring one thing on the car. I'm not checking every single, we have a ton of diagnostic information. We don't know what's going on. And then we have our team members that are there. We're all trying to figure out what's happening. And then we have our team members back home who are, not at the race, trying to know what's happening. How do you communicate that? So that's what I was trying to do. I need to make sure that we could contact our engineering teams at home because they're very knowledgeable people. They might know why this problem is happening. Get the car and fix the car because you're also, you're the race manager, like the team principal. You need to make sure that everything is working. So what we did is we ended up, I got all the team leads and I got all the technical engineers that knew the hardware of the car and the firmware to try and figure out what is happening, what is the error code, what does this mean. Turns out we had a faulty RAM stick, and when you migrate too fast, that RAM stick flickers and the car, as a safety, shuts down, hard brake so that you don't run into a wall. But that was not fun. That took around 2 to 3 days to diagnose and to fix, which when you have 5 days of testing is not good. So next is technical understanding. You need to know what you don't know. A TPM is not your lead engineer. I have a very strong, foundation in robotics. My background does come from perception and visual work. But I don't know everything about this race car. I don't know the low-level implementation of each aspect, but I have a very strong mid to high-level understanding. I know how things connect. I know how the stack works. I know how this car functions. And that's what you need to have as a TPM. I have a very trusted, chief engineer. He knows the car inside and out. He knows everything about it, how everything works, how everything connects. But that's his role. His role is just to do that. And my role is to support him in that work. And then next is, handling the planning and coordination so that the lead engineer doesn't need to. His job is not to do planning. His job is not to communicate with administrative staff, communicate with the organizers of the competition. That's on me. I need him to be able to focus 100% on getting this car to race as fast as we can. And then I'm also here to help troubleshoot. Uh, He doesn't know everything everything about everything, but he knows how to kind of direct himself. And I'm there to ask him and to question him and to make him think, but why are we doing this? Why are we doing that? And then that way we can get in the correct direction. And also architecture, like high level software architecture. That is kind of what I've been working on. That's a big part of my technical contribution to the team is how do we architect a software? That is where a lot of my, research experience does lie is in technical architecture. So it does help that that is also my responsibility on the team. And knowing what you don't know is very important because then you know what you need to learn. A big kind of learning curve that I had as an engine as a TPM was that I didn't know how to know what I didn't know. I know that was I said no a lot, but I hope you understand what I'm trying to say is that it's very hard to learn how to do something if you don't know what you're missing. So quick learning is a huge aspect of it. So an example is that when we were in Vegas, we were, having a chat, and then we had a thought. One of the engineers had a thought. What if we make a better raceline planner? A planner is a core part of your decision making. It's what's my path right now? What is the optimal route to take? As might come as a surprise, this car is not powered by AI. Most of this is actually traditional algorithms that are used and implemented in a pipeline together to get this car to function. So we had this idea for a new planner. Great. These planners generally take months to develop, test, integrate, and then race, and then collect data, test on the new data that we've collected by running it in the background, then deploy it. That's around a 4-month process. We had 5 days. So we got to work. A lot of Red Bull and a lot of Monster later, we got it to work really well. And my contribution was how do we actually get that into the pipeline? And then we had some small things here and there. When you've been sitting and working on a problem for 8, 10, 12 hours straight, they did not take breaks. You sometimes get a bit fuzzy, and that's where I was in to help kind of make sure they were, good, healthy, sleeping-ish, but also making sure that I could question them because they got groggy. They didn't always make the most sound decisions. I was there to question and ask them, why are you doing this? Why not this? And that's what happened. We actually got that planner implemented and we got it to run in the background to test, which was a huge step and pretty crazy to do in 5 days when this usually takes 4 months of an entire team. This was 3 guys. So next is KPIs. As I said earlier, that's a key performance indicator. And the big thing about KPIs and my kind of belief is I track things as quantitatively as possible. I need to be able to measure things. I'm studying engineering. I'm a numbers guy. I need to be able to measure that and see that. So you have quantitative data. That's like this data. You have, you have discrete states. You have, your progress, and when you measure progress, that comes down to a mix between quantitative and qualitative, especially on a research project where you're looking into new things. How do you measure how much you've looked into a problem? It's not, you can measure it in hours, but how do you measure that in percent? Because you don't know where the 100% is. So when you're working with quantitative data, spreadsheets are your best friend. Every single meeting I have, every task I've done, it's recorded on a document or a spreadsheet. My Google Docs is like tens of gigabytes of just documents. And so is, all the different platforms that I use. I have so many spreadsheets of meetings about different tasks. And it's all organized so that I know where everything is and I know what's happening. And it's usually indexed, by deadline and priority. That's generally how I like to do it because that way I know what I need to focus on. If a low priority task gets pushed back, that's not the end of the world. If a high priority task or a mission critical task does not actually meet its deadline, that's over. That's a big problem. Quantitative is where it gets really difficult. When you're describing a race car, let's say the car is on track, we're watching it to monitor it. How do you describe its turning performance? Is it, cars can suffer from oversteer and understeer. How do you describe that quantitatively? That's not that easy to do. When the car, we're watching the car's performing well. What does that mean? How do we actually explain that in a quantitative manner? We're researching, we're doing, as I said earlier, we're researching a new planning algorithm. How do you measure performance of doing the research on it? How do you determine priority? Priority is very, very important part of being a TPM, but how do you determine it? There's different methods that I'll get into, because priority does help when you get a qualitative task to turn it into quantitative. Priority is a huge aspect of that. And the biggest thing about a TPM is using your judgment. So quantitative, you here are kind of a couple samples of sample ideas that I use for quantitative measurements for more complicated projects and tasks and topics. So this isn't something that's just actually, you have a number that you can just see. This is how do you turn a task into quantitative. So there's deadlines, and using, we've been a team for 4 years. We know how long things take generally to implement. We know how technically capable our members are and how long it will take. So we can use our past history to determine how long it is going to take to do a certain task. And then there's, breaking it down by type. What that means is, like, I split tasks into their types. So that's, we start with the research phase, then you have the development phase, then you have the testing phase, so you test it on its own, integration phase, and then testing it within the entire stack in the background, and then deployment stage, right? And then you do that again. So now we want to implement a new planning algorithm, right? First, we do the research. We've done that. Now let's do the development. Okay. Development takes in, we need some perception data. Perception is what the car sees. So now we split it again. You now have, it's another tree. You have perception needs to do this, and the behavior team, our planning team, needs to do this. Then you go again and again, and then it goes back up. So now we've finished all the development. It breaks down all the way down. When you finish, it goes back up, moves to the next stage. That's going to be the testing phase. Okay, we need to test the perception aspect of it. So that's perception. We need to test the planning. So we're going to make we have simulated data here. We have simulated data here. Let's test it individually. Great, they both work. Let's now integrate them together. Okay, now we test it, together. So now it's, just a one thing of testing. And then we run it in the background. What that means is, let's say we have a planner that we know works. This planner has been proven, it works, it does a good job, but we have a better idea. We're not going to run and test a brand new planner on the track at 200 kilometers an hour when we haven't been able to test it on the car yet. And that's because you don't know what's going to happen. This is motorsports, this is a race car, things go wrong. So what we do is we run it in the background, and that just, it'll process everything. It just won't send controls. It won't send the car to do something. This just gets us as good, testing data as you can. This is one step before actually running it. We do that, we analyze, we tweak some things, we see how it works. If that's good, we'll deploy it and we'll run. And what we do, that's always the scariest time, is, the tension is high. We're testing something brand new on the car and it's going really fast. If it works, it's great. If it doesn't, why didn't it work? Let's go back, let's fix it and go again. It's a very iterative process. And then lastly, we have priority. So priority, as I said earlier, priority is such an important aspect of it. I like to have a couple different levels. One is, mission critical. Mission critical means if this is not done, if this is not complete, it will not run. The car will not run. We will not be racing. Then it has high priority. That means, let's say we are mission critical is get the car, test everything, calibrate the sensors, get it going. That's mission critical. Next would be, we want to test our new algorithm we've been developing for the past 6 to 8 months. So that's a high priority. We want to get that working. But if that's not working, we just won't get any new data, like in terms of new research data, but we're still going to be able to run. And then you have, medium priority, which is we have this newer thing we want to check. Low priority tends to be running something in the background. That's not actually high. It's not affecting the actual outcome of the car at this moment. It's going to change what's going to happen in 6 to 8 months, whenever the next race is. And then there's low priority, or sometimes research. I don't like calling it low priority because it's incredibly important, but it's not mission critical to the racing car at this moment. Because when we're testing, that's when I take off my research lead hat and put on my race engineer hat. I need to get this car to run and as fast as it can. And also a big thing is using your judgment. You're trusted to actually to have the experience to use your judgment and to be able to gauge things. Testing of something, like determining if something's mission critical, I haven't figured out a quantitative way to do it. I just know that if I can't get the sensors calibrated, I'm not going to send a car out there because the car will not know where it is and it will almost definitely run into a wall. So that's something I know is mission critical. And then the other priorities is based off of how how important it is to our research. Because at the end of the day, we are a research group. We do want to push forwards autonomy. This is the fastest autonomous racing competition in the world, and we are at the front of it. So we need to continue pushing it forwards. And next is the harder part. It's qualitative. So again, we spoke about priority. It's again a huge part of it. And then there's weights. I like turning qualitative tasks into quantitative by adding kind of weights to them. And a weight basically transforms an item from qualitative to quantitative. In terms of research, let's say I want to build a new tracker. A tracker basically tracks the other cars, and I know where the other car is and how fast it's going and where it's turning and where it's going to go based off of the perception. So based off the cameras, radars, and lidars, which are light radars. It just uses light to determine distance. So if I have that, how do I determine how far along our research is? What I would do is, again, use my judgment and use weight. So I want to find a new kind of algorithm or a new general idea. That's a pretty high weight. I'd say that's quite important to developing it and to doing the research. And then there's how to implement that. I'd say that's less important than finding the algorithm, but still pretty important. And then the smaller nitty-gritty details, how do you interface that with the sensor? That's very capable. We can do that. That's, I'd say, a low weight. And then I use priority. We want to get this running by, Las Vegas race. That's in January. That's been 6 months from now, let's just say. Okay, now I'll work backwards from there. And again, as you'll see as a theme in this is judgment, using your judgment to actually determine where things are and determine how important and how a thing does translate. That's a huge aspect that my job is to do, so that the engineering leads and my research, the chief engineer knows how to delegate his task and his work to the other members. So now that we've kind of gone over everything, let's go for a case study. And this is what actually happened in Vegas in January this year, which was a super exciting race at CES where there's hundreds of thousands of people come. And we're going to see how it goes. So it is a bit interactive. But first, the big thing that everyone needs to know about it is that nothing actually ever goes to plan. This was 2 or 3 years ago. We're racing. This is us onboard footage. That was completely not our fault. We were racing on a race line, and the other car decided they wanted to hit us. There's nothing we can do, and that is life, and that is motorsport. They bought us a box of pizza, so that's just what life is, and you need to know how to adapt to that. And again, as a leader, you need to make sure that that's okay. That does happen, and we do have contingencies in place. We do have to make sure we have the finances to take care of that, but also to keep motivation up. That's pretty, it's a hard hit to see all the work, get rammed into at, that was like 100-something kilometers an hour. It sucks, but that's life. So this is that was a couple years ago. This year, there have not been any crashes like that as of recent. So that's much better. But here's Vegas. So September 1st to January 2nd is development phase. We're writing, integrating, and testing code. What does that mean? We're going to chat about it in a second. And then it's January 3rd to January 10th. That's testing. We had 7 days of testing, and we need to test absolutely everything. And that's a lot more than what comes to your mind when you have to, do testing, because this is a very complicated system. So there's things you don't even think about. You need to test that the screws on the bottom of the computer are in place, because this car was traveled in the past year, went from Indianapolis to Italy to England to Indianapolis to another track to Vegas, and it's been flown, it's been shipped. You need to check all that. You need to check, it's a race car. You need to bleed the brakes, check the brakes are good. You need to make sure the tires are good, absolutely everything. So there's the motorsports, that aspect, there's the software aspect, then there's the, this is a software competition, but this is a race car. This is our, robotic application. We need to make sure the wires are all good. There's nothing arcing inside. As we'll talk about later, things do happen like that in a system like this. So here's a bit about the the development phase. There's 4 sub-teams. We have perception, that's everything the car sees. We have core, that's everything the car the data the car receives. So that's localization, which is where it is with respect to the environment. There, it's how fast it's going. It's how hot the temperature of the tires are, how hot the temperature of the engine is, how fast the wheels are spinning, how fast the car is going, all that type of data. Then we have our behavior team. So that's that's the kind of path planning. What do I do right now? Should I accelerate? Should I turn? Should I not? What do I do with all this information that I have? And then it passes into the controls team. That's your controller. If you're familiar with robotics, you know that there's various types of controllers. A popular one is MPC, Model Predictive Control. That's just a way to, if I want to go straight and the car is turning left, veering left, I need to correct myself. If you've driven, you kind of know that sometimes you have to adjust the wheel because the cars should be going straight, but it's not, because it doesn't always do that. So that's just what the controller does. We have 5 different projects going on. We have 1,500 commits. We have 2 events that we had to kind of prepare for, and we had 4 months to do. So what do we do? How do you kind of do all that? There's the logistics, there's communications, there's administrative work, and there's actual technical development. That's a lot to do. And we're just going to focus on the technical development part. So a bit about the work. I'll go from the top. So that's using cameras to identify where the other cars are and where they are with respect to us, because you've got to know where that is so you don't hit into us. I guess the team that hit into us didn't have a good tracker. But then that over there, that is a LiDAR point cloud. A point cloud is literally just a cloud of points, and you know the distance. And if you use radar, you can actually, instead of using the change over time from distance to get their velocity, and then the change of that to get their acceleration, radar you can directly measure speed. So it's a lot more actually velocity. So it's a lot more accurate, it's a lot more precise. This is a learn-based planner. So currently all the planners are algorithms. It's not AI. It's I want you to do this when this happens. This is a learning-based planner. That is something that someone implemented that we are looking to do. It's using machine learning to actually drive on a track. This is using a very strong racing sim that can actually do a really good job simulating the environment. And then lastly, this is us driving in Goodwood. So that's the mapping side. This is a hill climb. As you can see, this is not a traditional racetrack. It is super thin. We're used to going on tracks that are easily six car widths, wide. This is 1.5, maybe 2 if you swish. That's really, really hard to do when you're traveling at speed. So this isn't a super high speed, but when you get fast, it's much harder. So that's a sample of all the projects that we had going on. So how do you actually develop it? So I'm going to ask, if anyone wants to do some back and forth about what do you think is, of these 4 projects, we have our tracking, we have measuring the velocity of the other cars, we have a new planner, and we have your localization. That's where you're. Who do you think? If you have to order these in order of priority? Each priority gets one thing. What do you think is most important? Does anyone want to volunteer? Go for it.
The tracking.
Yeah, that is completely correct. Tracking is, in my opinion, I want to say I come from a perception background, from the perception team, is the hardest part of this competition. It is very hard to do this at extreme high speeds. That is way faster than you think. I believe that's around 180 kilometers per hour. It's really hard, and you need to get really precise data really, really fast. Okay, now that we know where we're tracking the car, what would you say is second in priority? Does anyone have any ideas?
The planner, I think, the bottom left.
So the thing with the planner is that it's an idea for research. It's not actually, we're not testing it yet. So I'd say I don't think it would be that high of a priority, but do you want to elaborate on why you think it should be high priority?
I thought it was like the race line and like the path the car actually goes on. So like that's like next important
yeah,
where everything else is.
Yeah, for sure. So a planner, if we were to be implementing, a planner that or tuning a planner, it is, yeah, I'd say it is probably number 2. I guess I should have clarified in this case, this is a completely brand new planner, rather than tuning of fixing something that we already have working. As this is a new planner, it's in the research phase, which is why it wouldn't be such a high priority, but that is 100% right. If we did have, a planning on one of these examples, it would be number 2. Does anyone have any ideas for what would come after the perception in this case?
Localization.
Yeah, spot on. You want to know where you are. Because we have snacks, we're on the track for 12 hours a day. We have snacks, we eat baby carrots. We have baby carrot levels of precision. That means we know where the car is anywhere on this planet within 1 baby carrot, which is pretty good. But how do we do that? You have 4 GPS antennas, which is primarily what we use. It's called GNSS, which just means instead of using 3 different GPS satellites. It uses multiple, you just get multiple sources of information, you get a better idea of where you are. But how do you actually fuse that all together? And then you can actually get even more complicated by connecting that with the map of your environment. That's exactly right. It is extremely important to know that, because let's say we're in the front or we're by ourselves, we passed the car. How do we know that there's, we can use perception to determine a wall, but what if where the road gets kind of, it's banked, well, it's flat. You do not want to go half on bank, half on flat. These cars are not meant for that, because the suspension is super rigid and it's super low to the ground. You're going to scrape the bottom of your car completely. That's bad. So that is completely right. You want to know everything about where you are. And then we'll go on to the next one, but then would be kind of the velocity estimation, because we can determine that through cameras and through the instead of using radar, through LiDARs as well, which ours is actually probably the best in the competition at this point, which is pretty good. So we don't need to, we do want to get better. We are working on fusing it all together, but it's not as high priority. So I'd say that goes three, it's low priority. And then would be this research of, can we make a brand new type of planner that's never been implemented at scale at this, because it actually has not been implemented anywhere in these similar competitions. But the only one that I know of that is for sure neural network based planning is the Tesla autopilot, which we do have some of the engineers from that team who've interned there on ours, which makes sense. But next is testing. So in Vegas, we had 6 days. We have 3 garage days. That means we have a chance to work with the car. The car just is not going to be racing on track. We didn't rent the track that day, but that's all the days we need for sensor calibration and all, and checking our RAM because the RAM's not working. That's great to have on a garage day because you're not losing track time. Tracks cost tens of thousands of dollars for a day, if not more. The more popular the track, the way more expensive. So you need to maximize the time on it. If we have 20 minutes, we're going to use every single second that we have. So what we did is we have testing, and we want to make sure that we don't want to change code, because we learned through our experiences. We once changed code a couple of years ago at 3 a.m. the day before a race. We crashed. That's because we changed code 3 a.m. before a race, and that's not great because you're on low speed. So we've since then implemented code freezes. So what we did is we implemented a code freeze about 3 weeks before before our first garage day. So that was in I think the first or second week of December. What a code freeze it means is that no new code that is going to be run on the car is going to be pushed after this date. Obviously, tuning and fixing things is fine, but you're not making, that's only tuned at when you're literally with the car, you can tune something. That's it. And the reason for that is you don't want to make rash decisions. We want to have more than enough time to test everything, to make sure everything's working. And because we have different simulation tools to test, the different components of it. So there's all that testing. And then, as we said earlier, there's so much to go into testing. As we saw earlier, stuff does not go to plan. We were out of commission for 2.5 days because our RAM chip wasn't working. That took a while to figure out because we thought, is it our software? Okay, is it the car? Is something wrong with the car? Nope, the car seems fine. Is it the CPU? Is it the GPU? Is it the motherboard? And then we figured out it was a single RAM stick because of an offhand comment that someone made. We decided to push into it and see what happened. But that's life. But yeah, so this is 1 day this is kind of everything we needed to go over. We're not going to go over all of this, but I'll ask the question: what does anyone think a space drive is? Anyone know? Yeah, I had no idea when I first looked at the name space drive. All it is it's kind of the back end controller, I guess, of the car. What that means is it's the piece of hardware that just lets everything work. If it's not working, car doesn't work. It's another safety feature that's in this car, but I had no idea what it was, and I had to learn quickly because this was my first time leading this team on a race. So we have all these things, but how do we actually, this is just one kind of screenshot. It's about 2 to 3 times more than this of things to check, but how do we test it all? We don't have a lot of time. So here I'm going to just kind of, again, the same thing as we were going over earlier. I'll move. So we have a new agent tracker, as we saw earlier, from perception. We have a new pathfinder for behavior. We have a new car controller from the controls team. We need to calibrate all the sensors. We need to verify if the previous generation of the stack works. Why we do that is, let's say none of our new stuff works. We still want to race because that data is so precious and also super expensive. So we want to make sure we can get that data no matter what. And then safety, we need to pass safety inspection and test everything for that. That means if we don't pass safety, we don't get a race, which makes sense. Safety is a priority. So I'll kind of go again. I guess it's hard to see with the light. This says mission critical. The car will not run without it. Then you have car will not perform well without high priority tasks, and research goals that are not met without this. That's a low priority task. Does anyone have any idea what are there are a few things that are mission critical. Anyone have any guesses? Go for it.
The safety inspection,
Yep. What else do you think could be mission critical?
sensors.
Yeah, we need to calibrate sensors. I'd say they're equally as mission critical because we have no idea if it'll work. We can't pass safety because we can't get on the track if we don't have our sensors calibrated. That means making sure that the GPS all know where they are in the car. We know where we are within one baby carrot. And also we know where the cameras, we can determine how cameras work. So cameras, if you've ever seen a fisheye lens, they warp things. It's really hard to actually work with data that's completely warped, and we need to make sure it's all in the same space. So what that means is I know where I am in this room, but I have a really bad kind of global idea. I have no idea where I am in Waterloo. I have no idea where I am in Ontario and so forth. We want to get all that data into one reference frame. So the car knows where it is, but within all those different frames or like reference frames. That's what calibrating sensors are in safety, just passing safety. Who has any idea what a high priority task in this case would be? Anyone have any guesses? Over.
It's like bird playing previous generation.
Yep, that is spot on. We need to make sure it works so that, as we said, the data we collect is super, super valuable. And I'd say probably also a high priority task in this specific case would be our new agent tracker. We had a new, very, very fancy tracker that let us trail super close behind the other cars. So a big thing in this competition is you're passing one another. You need the closer you can trail behind the car, the less distance you need to pass them, right? If you don't have a really robust tracker, you want to keep your distance because you have more time to rely on your controller to adjust. Our tracker is super good, which means we can trail around 10 meters, 15 meters behind a car. When you're traveling at 200 something kilometers an hour, that's like a fraction of a second in terms of trail distance, which is super, super tight. But we were confident and we were happy to do that. So that's why we wanted to make sure it was a high priority task, because we didn't feel comfortable trailing at 10 to 15 meters without that in place. And then low priority would be the new path planner. We ran that in the background, as we said earlier. That's to collect data on how it performed, and then we can see if we can implement it in the future. And also, the new car controller. That was also, we ran it in the background. That's a new type of controller and planner mixed together. Because it's super, super complicated, we ran it in the background, and it was more of a low priority task since it is more research based. And we needed to test it. This was probably one of the only chances we get to test it at this speed with multiple agents. So that's why it was low priority. And now, race day. To this. So all your work that you've done as a TPM in development, in testing, in management, all that comes down to this. And this is one of the reasons why we do this. Who wants to guess how fast that is actually going? I know it's hard because it's zoomed out and it kind of doesn't look that fast, but who knows how fast that was? Who wants to make a guess? Anyone want to guess how speed? Go for it. Oh, down that, yeah. That pass was around, I think, 220 kilometers an hour, that back stretch is like a couple hundred meters, I think. So that you saw how fast we just passed around them. And when you're doing that, you also need to make sure you're correcting for the bank of the track, and also not hitting them, as we saw in the previous video. Don't want to hit someone unless you want to buy them pizza. So yeah, thank you everyone for showing up and for coming. Does anyone have any questions? Yes.
Dashboard to make a decision, or the dashboard just say we're not going.
It's
This is high speed and it's a lot.
It's 100% human judgment. We have a dashboard that will give us a ton of information. In Vegas, unfortunately, after that pass happened, we ran into issues out of our control. Our brakes started failing and our engine started knocking. If you've ever heard a car hearing a knocking sound in your engine, is a terrifying sound. We heard that And we were able to identify that like that because we saw on our dashboards spikes and breaks. So that's not good. And then we audibly heard knocking and we saw something wasn't right with our throttle. We give throttle, the car wouldn't go, so we give more throttle and then we jump. Something's wrong. And then it was myself and the chief engineer were like, I don't feel comfortable. I don't feel comfortable. We're calling it, let's bring it into a pit, try and fix it before we can go again. But it's a lot human factor. Anyone else have any other questions?
Are there any like standardizations that like all the teams have to go through? Or like I know like the passing on that was just kind of like a straight track, but like on like that fun tracks like Monza, is there like specific passing zones or like where like a car has to like give up the racing line or like something?
That's an amazing question. There are only certain passing zones. So the way this works, it's a bit of an interesting way is that you have a attacker, that is the car in the back. That car, sorry, is trying to pass the car in front, your defending car. You're not allowed to leave as a defending car if you're on your race line within, we have some leeway because it is a robot in the field. It's not actually going to stick to the line exactly. You're not allowed to defend the line in terms of changing lines to block the other car. Right.
Like you can't do that.
Yeah, you can't do that. But there are areas where if you're the attacking car, you're on the inside line. The defending car is also on the inside line. You switch to the outside pass and switch in. The team that won in Vegas did exactly that on the front corner and dive bombed into the corner, which was crazy to see. But yeah, so you do have to yield. And you have to yield. It's a lot of trust. We've been working with the same teams for around 4 years. We're all researchers. We all know each other. We're all not going to maliciously try and damage someone. But it does happen. A lot of it tends to be mistakes. So in Vegas, in one of the teams, they had a bug where they were defending, so they're for car in front. They kept accelerating more and more and more. So the car behind them could not pass. So what they ended up doing is they called it themselves, saying something's not wrong, something wrong with their stack. Something's going. We know you have a feeling of pit in your stomach. Something's going to happen. Pull the car in because it's not performing well. There's constant communication between the teams that are racing on track and the race control. And also teams, we don't have a dead man switch when we're racing. It's fully autonomous. We can command the car to stop if we feel unsafe. Usually we ask for race control because it's polite. But yeah, so in Monza, for example, the way it worked when we were there was the first time we were at an autonomous race was on Monza. It was a time trial. As we discussed with the organizers, the goal is to have it with certain passing zones on the streets, or preferred passing zones, but you can pass everywhere. Odds are these cars are not going to pass on like a chicane or something like that. That's a great question. Yeah, so this is the spec series. These are Indy lights and Indy cars. This is the previous generation of Indy car. They're all within the electromechanical threshold the same. But yeah, they're very similar. They all have a top speed. I think they got upgraded, so their top speed is around, I think, 190 miles per hour. Previously they were 184, but they're all, yeah. You can configure the car slightly in terms of the setup. So the angle of the wing and how much you want your suspension to bounce. But other than that, they're pretty much the same. Yeah, that's a good question.
First of all, great workshop. My question was, I think a couple slides back, you talked about like weights and stuff. How is that different from like priority?
Yeah, so priority, I'd say is about being related. I do priority as mission and how it relates to the mission of the team engineer, or the race engineer of getting the car to run and function. And weights are more to be able to measure qualitative tasks. So in terms of a priority for research, I'd say finding a new algorithm and figuring out how it works is I'd say it's a low priority, right? It's not going to take precedence over calibrating sensors, but I would weight finding which paper, let's say, you want to implement, and weight that higher. It's kind of a subclass of priority. You could see that. It's a great question.
Makes sense. And then like going back to like that slide of like you showed kind of the example of like high priority, low priority, like a sample like things that need to be done. Yeah, I mean this one. Is this like actual like snapshot of like what it actually looks like, or is that how's it actually like?
This is from the track. This is from our a very simplified version of the track plan. This is something that it might look like, but this is a high level overview of our idea, and then it gets refined, and each of these has either a spreadsheet or a very long Google Doc, everything that has to go with it. I can't share that because that is IP.
Yeah.
But yeah, so this is kind of what it might look like. This is a high level of what our maybe idea was to qualify and test a bunch of stuff. As you know, things don't go to plan though, so it's on the fly being changed. And we do account for these things not working, but we do want to plan for the best case or hope for the best, plan for the worst. Yeah.
And then like in like a meeting, how would you kind of like that you just kind of go fix it?
So this works by first myself and the chief engineer, we will have a one-on-one, this is over the course of like months, like right, 2 months before, we'll have hours of meetings from starting from high level to mid to low level of everything that we need to get the car to run. This is something where, it's a lot of trust that this chief engineer knows what they're talking about, and they, so it's a lot of trust, it's all that. And then we get that, we have a massive, usually it's a spreadsheet, which is huge. We break it into the different sub teams. We talk with the sub team leads because they're subject matter experts in that to make sure it's all correct. We go over that, and then we know, okay, we know everything. Here's what we need to do mission critical. That's always the first thing that I do. I ask them, okay, what do we need to get this car to run with our stack that we know that works? Nothing new, stack that works. How do we do that? Okay. Then around, it's usually 2 to 3 weeks before the race, we get what is safety. So there's different qualifications. Safety is to be able to qualify, and qualification is what order you are, like what speed you are. We always want to qualify first, right? So then we go, okay, we need to do safety first because we can't test anything without safety. Do that, then we go over it, and it just takes a lot of time. But we have 4 years of races, and there's 2 to 3 more races a year. So we have a lot of data to go on and use. But it's a lot of.
That makes sense. And I assume there's some sub teams, so you kind of meet them separately.
Yeah, so generally I tend to meet with the sub team leads because I don't need to have a low level. I do like to pop into those meetings because, I'm an engineer, I'm studying engineering. I like the technical, but I don't always have time for that. And yeah, so it's all about meeting and communication, knowing what needs to be done, what resources. If we need more compute resources, that's my job. I need to be able to get it for us by any means necessary. Yeah. Any other questions?
Yeah, just curious, what's the simulation software that you use? Like, are there a lot of challenges like calibrating?
Yeah, so the biggest thing, one of the biggest challenges in like autonomous robotics right now, that are being deployed, so something that is a complicated system like this is sim to real gap. The sim to real gap is huge. You cannot model everything, and it's just really hard. They're trying to make better models, but it's really hard. So we kind of have our own spin on something called Autoverse. It's by the Autoware Foundation. They built it specifically for this challenge. It's good for testing planning and controls. It's not good at testing random noise. We can't test perception, which is everything the car sees. We test on recorded data. So we record every single thing. We have around 50 terabytes of data. And yeah, so we can test the data. We can test a new tracker based off of the cameras of a previous race, which is sufficient for testing, but we can't really do integration testing. Yeah, some teams use their own custom software. In the video of the learning-based planner, that was actually somebody who built a plugin for Assetto Corsa, which is a racing game, but it's also a really good physics simulator.
And is that like multi-agent simulation?
Currently, we can do multi-agent simulation. One thing you'll see is there should say Ghost somewhere up there. Testing on Ghost. Yeah, so what the Ghost means is that when you're doing qualifications, sometimes you don't have the time, you don't have the logistics to one of the qualifications is to pass another team at over 100 kilometers per hour, which for us is slow. Sometimes, let's say it's a brand new team, you don't want to test that with them because you don't know how they're going to do. So what you could do is test with a Ghost. What that means is you're not simulating the detections of another car. So we already have that in place, so it's quite easy to plug it into the simulation software. Does anyone else have any other questions? Yes.
With all the different variables, like for each race weekend, like humidity, like air pressure, and like even like track, grip, how do you determine how does the computer determine like a risk percentage that it's willing to take and like overtake another car? how fast it's going to go.
Yeah, so that's I guess risk is out, we determine that. It's a bit kind of rudimentary in the sense it is sort of hard coded as to how much we're willing to risk. We tend to play on the conservative side because for students, we can't just buy a race car, because they're expensive. These are $1 million cars. So we play a bit more conservative, but the way it works is that we see how we always do slow, we build up, we do a slow run. How's the car performing? Okay, we need to make it, adjust this, tune this to make it, there's not much grip. Okay, we need to tune the controller for that. And we change our velocity profile. What that means is how the car, what's the car trying to do over the track? We can tune that and change that. So if we notice track conditions are awful, car is slipping, we're just gonna go back a little. We're not gonna push so hard. The controller does do a good job of adjusting for that, but at the end of the day, we don't want to risk the car. But we're not super conservative. We will push the car. We will go as fast as we can, within limits. That's a great question. Yeah.
And then another question more on like the leadership side of
Yeah.
things. For your team, for this team specifically, like did you form the team yourself or did you kind of join when the teams are?
That's a great question. Yeah, so I did not found the team. I joined as a perception engineer. I was an engineer on the team for around 8 months. I got very lucky. I got to go to Monza, Italy to see how the car. That was my first time actually seeing a car, seeing a race. I was like, oh shit, this is pretty cool. This is an actual race car. I want to do this. I want to get more involved. So I committed a lot more to the team. I took on more responsibility within perception, within the biz ops side of the team, within management, and I just moved my way to becoming the team lead now. Yeah. Anyone else have any other questions? If not, thank you guys all so much for hopping in. Yeah, if you do want to connect, you can find my email. It should be on the information board. Yeah. Oh yeah. This was posted on our YouTube channel, by the way. Yeah, so that happens. Yeah, if you do want to stay in touch, you can find me on LinkedIn at Idam, or you can email me. The email should be posted with the hackback. But yeah, thank you all for attending.